Yep. Yeah, I think we should start. Yeah. Our next speaker is Yuya Tanizaki. He will be talking about topology of SU and over Z and landscape fields. and generalized Hooft anomaly.
Yeah, thank you for introduction. And I really thank the organizer having this workshop. Yeah, I really learned a lot of things, so yeah, I enjoy a lot. And also having, I'd like to thank for giving me this opportunity to talk about my recent work. So talk is about some topology of lattice gauge field and its relation to recently discovered anomaly. And it is based on this work in collaboration with Hiroshi Suzuki in Kyushu University and his student Motokazu Abe, Soma Onoda, and a postdoc at Osaka University, Okuto Morikawa. So this is a conference about confinement, so I don't have to say much about this introduction. But the talk is about 4D and YAML theory, and it's a very interesting theory. It's a fundamental theory of strong interaction, generates an exponentially small mass gap, so having a mass gap out of basically nothing. And also this shows the confinement of quarks. So if we put the color degree of freedom, they are confined with electric strings. And these are basic interesting property of SU YAML theory. But recent days we have uncovered that so confining vacuum of YAML theory have more rich structure than we have expected. So to talk about it, so let's add this kind of topological term to the SUN YAML gauge field. So in continuum field, as a continuum field theory, SUN gauge field has a non-trivial topology because of this discretized topological quantity. And this allows us to introduce the theta angle to the YAML theory. And the path integral is given by this kind of thing with YAML kinetic term in, and you can add this theta angle term. And in this sense, so YAML vacuum has a continuous parameter called the theta angle. And because of this quantization property of topological charge, so theta is a 2π periodic variable or 2π periodic coupling constant. So it deserves the name of calling it as an angle. And this theta angle has this kind of 2π periodicity, showing that so partition function with theta has and partition function at theta equal 2π are basically the same. And this tells us that so YAML theory at theta and theta equal 2π are unitary equivalent. So, but this is not the end of the story. So this YAML theory has a symmetry called the center symmetry, or recently it's more sophisticatedly called as the N1 form symmetry. And regarding it as that kind of sophisticated version of the center symmetry, and we can couple the background gauge field so for the center symmetry, and you can study the partition function, including the background gauge field here. And here, 2π periodicity of the theta angle is lost. So if we compare the partition function at theta and theta equal 2π, there is an extra contact term that depends on the background gauge field for this to achieve this equality. So although YAML's theory at theta equals and theta equal 2π are unitary equivalent, but vacuum at theta and theta equal 2π are distinct as symmetry protected topological phase with center symmetry. This relation is found by this gentleman, so Zohar and his collaborators. And Eric talks about its outcome as a semi-classical realization as a first talk in this day. And we have seen that, so for example, at theta equal pi, we have twofold degeneracy at the non-perturbative level for the YAML's vacuum. And this is found already about 6 years ago. So this relation is 6 years old. And I think many of the participants here are benefited from have a great benefit from this kind of exact relation of the YAML's partition function. And we can study, we can uncover many things on YAML's confining vacuum, just having this rigorous relation for the YAML's partition function. But let's stop a bit. So this key relation is derived from analyzing the smooth and classical gauge field. So basically, this derivation comes from the fact that so YAML's topological charge with Hooft twisted boundary condition has 1 over n shift. So topological charge is shifted by the fractional value under the presence of Hooft twisted background, Hooft twisted boundary condition. And that 1 over n shift of the topological charge affects this counter term for comparing the YAML's partition function at theta equal 2π. So this relation is basically was derived from that observation. But then here we have a natural question. Does this important relation hold at the renormalized and non-perturbative quantized Yang-Mills theory. So this is a question I'd like to answer here. And the answer is yes, it does. It does hold as a rigorous relation for the quantum Yang-Mills theory. And what we will do here is so we will extend the work of Martin Lucia in 1982. So in that time, so Martin derives or introduces the notion of topology in lattice gauge field. And we extend this work for SU and gauge field, now coupled with background gauge field for center symmetry. And we define a nice topological charge that is local in lattice sense. And this topological charge is physical in the sense that it is SUN and center GN1 from gauge invariant. And this topological charge has an expected quantization property. So this topological charge is basically quantized integer, but under the presence of V field, it is shifted by 1 over n. That is completely characterized by the background gauge field for center symmetry. And as a corollary of this useful property of Yang-Mills lattice topological charge, we will show that this relation holds at the lattice Yang-Mills theory at finite lattice spacing. So this kind of relation could not be spoiled by lattice gauging, lattice regularization for Yang-Mills theory. So basically, this is a punchline of my talk. And from now on, I'm talking about how we derive or how we define this nice topological charge on the lattice. Okay, so before that, so before going to our work, let me tell a brief idea of what Lucia did in 1982. So in continuum field theory, so that this topological charge is classifies a homotopy class of SUN gauge field on continuous space-time. And this is roughly a total derivative quantity. And that suggests that so this topological charge depends only on the transition function or boundary condition of the gauge field. And the question is, how do we derive that kind of twisted boundary condition for SUN gauge field out of this lattice setup? So in this lattice setup, so SUN variables are living on the link. And basically, this is the whole quantity to define the SUN lattice regularization. But in continuum, what we want is, so we have patches, and there are many patches to cover the whole space-time. And there is an overlap. And one form gauge field are living on this patch. And on this overlap of two patches, we want to connect the description of two gauge field, and we need a transition function that connects the gauge field on one patch and the another patch by this gauge transformation function. And in this kind of overlap, there are several ways to connect gauge field here and gauge field here. And that requires that this SUN transition function has to satisfy this kind of cocycle condition. And having this nice transition function, you can compute the topological charge. And the question is, how do we obtain the data of this transition function out of this lattice data? And what Lucia did is, so this kind of nice topological charge, nice transition function can be obtained out of this SUN link variable if it satisfies what is called as admissivity condition. I will go back to this, what it means later, but so basically this is what Lucia did. And what I will do from now is to extend this work to the case of SU and Yang-Mills theory coupled to background GN gauge field, background center gauge field. So our setup is we consider SUN link variable living on this kind of link. And in order to introduce a background gauge field for the center symmetry, we also introduce this GN Zn valued bracket variable that is living on this bracket. And our Wilson gauge action can be given by this. So out of this SUN bracket variable, by multiplying its SUN link variable and multiplying it in this way, we define the SUN value bracket. This is roughly saying that this is the exponentiated version of the SUN field strength. And we basically take a trace to define the field strength square as a Wilson action. But in addition to this, under the presence of this Zn valued bracket variable, bracket gauge field, we attach this Zn phase in this way. And here, so I will assume that this Zn valued bracket variable does not have any local dynamics. So I'm assuming that its field strength is 0. So basically, I'm saying that this Zn valued field is flat or does not have any lattice monopole here. And a notable property of this Wilson action coupled to this Gn background gauge field is that so this is invariant, of course, invariant under SUN gauge transformation. And also this is invariant under what is called as Zn valued Zn one form gauge transformation. That acts on this background gauge field as shifted by the total derivative of Zn valued total derivative of Zn valued one form field. And on the link variable, so this Zn valued transformation acts really as a center transformation. So this manifests the fact that so this background gauge field is really the gauge field coupling to the center transformation. Okay, so here let me talk about what about admissibility condition. So this link variable, the space of this SUN link variable is just a space given by SUN to the number of links. So basically, this is a connected space. So that means that any configuration, so any lattice configuration can be continuously deformed to the trivial configuration. So unlike the case of continuum SUN gauge field, any configuration are continuously connected. So of course, without importing any condition, that means that we have no notion of the topological differences for any lattice configuration. So unlike continuum case, in this sense, lattice gauge field has no topological sectors. But this is not the whole story, and this is what Martin Lucia pointed out in 1982. So in order to study the confinement and reproduce the continuum limit, what we want to achieve is the weak coupling limit. Then we generate the exponentially small mass gap. Then looking at this action, and this beta is basically 1 over g squared, that roughly says that so this bracket variable should be sufficiently close to the identity. So dominant configuration of the path integral should be restricted to these very, very tiny regions. And that means that, so, okay, then let's try to restrict your configuration of the path integral in this small region, while now, unlike here, so we just take some order 1 number, which is just roughly 0.1. It just needs to be smaller than some pi or something, but it can be taken to be independent from coupling constant, lattice spacing, lattice sizes at all. And if this lattice field strength is smaller than this some small order 1, smaller than this order 1 number quantity, then let's call this gauge field as admissible. And what we will do is instead of performing the path integral over whole region of the SUN link variable, let's restrict the path integral into this region. And since this region covers this dominant configuration, it would not affect the continuum limit at all. So this is just an irrelevant deformation of the lattice Yamu theory, at least in the continuum limit. And just having this admissible condition, it will turn out that we can now introduce a topological now we can introduce the notion of the topological sector by having this admissible condition. Yeah. And now, so I will impose this condition from in the talk in the following of my talk. And from now, so I'm now trying to construct the transition function out of the data of SUN link variable. And I try to draw a nice figure, but it turns out to be complicated. So instead of showing this, I think lively drawing the same figure here would be more convenient. So I will do that. But before that, so let's introduce the notion of the complete axial gauge. So in order to define the patches and transition function, we have to fix the gauge so that we can reproduce the notion of continuum gauge field out of the lattice. So this kind of link variable can have order 1 fluctuation. So basically, so this kind of link variable does not have a good notion about its close to. So without having any gauge fixing, this U can be arbitrary, so it's not close to 1. So gauge field for this link variable does not have a good continuum notion. So what we do is for each point, we take the complete axial gauge. So drawing this kind of lattice. Yeah. And let's call that this point is N. And let's draw that. So let's draw a tree so that it does not have any closed loop, something like this. And what we do is, so if we introduce a notion of complete axial gauge for this site N, and that is described by this subscript. And for example, let's take a link variable connecting AB in this context. And what it did is, so first what we do is connect starting from N, go to A, and consider the link variable AB, and from B along this red path just coming back. And in this case, so this is just 1. So if you take the points A and B within this tree, so this link variable is just 1. And in this sense, this is called a complete axial gauge. But if we take another AB, which does not belong to this red curve, for example, something like this, A and B, then in this case, what we will do is first we want to connect N and A along this red path. So I forgot to wait. Yeah, so this should not be red and this should be red. So first go from N to A, so like this. Then connect A and B as the link variable and coming back. So in this case, UNAB is a bracket given by this one. So point is, so in this complete axial gauge, any link variable is always a loop starting from N and connecting A and B and coming back. And under the presence of admissibility condition, this is always close to 1 plus order epsilon. That means that so gauge field in this axial gauge is always small, sufficiently small enough. Yep. Okay, so. Exactly. So in this case, I don't think, wait. In this case, I don't think so. Or maybe it is there is a gauge transformation at N can act as a global transformation, but here, so here we just multiply just a link variable along this path, so there is no ambiguity in this construction here at least. Yeah. So in this way, so we introduce a bracket, a complete axial gauge. And since this is always a loop, so under the one form transformation, so if we attach sufficient number of Zn valued bracket variable, for example, filling here, then this kind of complete axial gauge link variable can be made completely one form gauge invariant. And now, so here in this, now we define the completely axial gauge at each site. And now we want to define the transition function. So what we want to do is, so if we have 2 patches, and in this overlap, we would like to define the transition function. So, and the way to do it is, for example, let's call this is A and B. And let's consider that so this link variable now have 2 representations. So it can be represented by complete axial gauge starting from this side, A and B. But it should be gauge equivalent to another completely axial gauge starting from this site N. And so this should be gauge equivalent. That means that so this should be equal by some gauge transformation B tilde B inverse, and yeah and mu and mu. Yeah. And in order to do it, so we should compare two paths. So UNAB is just this cycle, just this loop, and UN minus mu AB is wait, it's something like this. And in order to, and these two are of course not equal, but if you multiply the transition function, something like going this way and then coming back, then these two passes are cancelled out. And this part corresponds to this transition function for the first one at site A. And in order to obtain this path, we just need to attach this one. And this corresponds to Bn minus mu at site B. So since UNAB and UN minus mu A hat AB gives a completely axial gauge in different parties, so this gives a nice notion of the transition function here at the side at the corner of this overlap region. And this transition function turns out to satisfy a nice property having this kind of cocycle condition at the corner. But the point is, so here transition function is still defined only at the corner, and all the construction for here doesn't care about the admissibility condition. But what we actually want to do is to define the transition function over the whole overlap. So transition function at the corner is of course insufficient information. So we have to interpret this transition function into the whole overlap region. And this formula is actually so complicated, but so using the data of transition function at the corner, you can interpret that transition function to the whole region of the overlap by having this kind of interpolating function without violating this cocycle condition at all. And the formula of this interpolating function is very complicated, and I do not have a good intuition under it. So please ask Martin Lucia for the intuition behind it. But if you believe this formula and use the admissibility condition, then this interpolating function has a very nice property, and this cocycle condition turns out to be true for all the region inside this, for all the overlap region. So in the case of, so under the presence of B field, basically all this link variable has to be constructed in the one form gauge invariant way. And but if we impose manifest one form gauge invariance at the same state at the every stage, then Martin's construction turns out to be nicely extended to this setup. Yeah. So admissibility condition. So here, so this y is a coordinate for this cube. That is a continuous variable within 0 and 1. And in order to define this interpolation, you have to take this fractional power for unitary matrix. So that is basically saying that you have to perform the inverse log transformation from exponentiated unitary matrix to traceless Hermitian matrix. But for that inverse transformation, some kind of the admissibility condition is necessary, or it should be sufficient close to the identity region to perform this, to take this fractional power. So in this interpolation, admissibility condition plays a key role. Okay, then so everything what we have done is, so out of this lattice data, we now construct a nice transition function that defines a continuous SUN over GN principal bundle. And now using this transition function, so you can compute this kind of local topological charge. And this now defines a total lattice topological charge out of lattice data. And since in the construction of this B transition function, we only need the information in the adjacent cells. So our construction is completely local. And it turns out that every step is manifestly SUN gauge covariant and GN1 form invariant. So this construction gives gauge invariant lattice topological charge. And now, so with using the data of the cocycle condition, just open Van Baar's paper, and then it turns out that so this topological charge has integer quantization with this 1 over n fraction shift. And that fractional shift of the topological charge is completely controlled by background gauge field. Yep. Yeah, so here, so if we in order to get this fractional part, so there is an ambiguity for the lifting to the integer. So this B is just GN gauge field, but and in order to get this kind of expression, we need to take the integer lift to integer valued cochain. And in order to be completely invariant under that choice, this couple one product is important. Yeah, but yeah. Yeah. That does not. So this decomposition is not invariant under that lift. Yeah. But in modulo 1, this is a well-defined one. Yeah. So under the change of the lift, these two are exchanged a little bit. Yeah. Modulo 1. Yeah. Modulo 1. Yeah. And having this relation, now we can obtain this relation as a Yamu's as a lattice Yamu's partition function at finite lattice space. Okay, let me summarize. So what we have done is so following Russia out of SUN gauge field coupled to GN background gauge field with admissibility condition, we now define the well-defined local and gauge invariant topological charge. And our construction is basically the extension of Russia by coupling the GN background gauge field. And by making the manifest one form gauge invariance at the every stage of his construction, all the proof turns out to be extended nicely. And the take-home message is now this relation is derived as a lattice regularized partition function of the Yamu theory. So even if you are a hardcore latticean who are not so much care about continuum, now this is your tool too. Okay, and possible future direction is so here we extended Russia's geometric construction of the topological charge under the presence of this GN2 form background gauge field. But that geometric lattice definition does not necessarily have a close connection with index theorem of overlap fermion. Or at least what I mean is not at the current stage, a connection between index of overlap fermion and this geometric topological charge is not known. So in order to extend this study or this anomaly to the lattice adjoint QCD, chiral anomaly of lattice adjoint QCD, we need further investigation on lattice topology of gauge field. So this would be a good future work for us. Okay, that's basically everything. Thank you very much for your attention. Yep.
Questions?
But practically speaking, so having admissibility condition, so basically acceptance rate of Monte Carlo step could be delayed. So yeah, so you have to pay some cost for yeah.
They usually simulate normal, but they cool if they're gonna use it.
Right, but precisely speaking, so under that gradient flow step, so maybe topological sector could be ambiguous or something. So as long as if we only pick up admissible configuration, and if gradient flow step keeps that admissibility condition intact, then that topological sector should be always the same. But yeah, in general, it's not so clear. Yeah.
transmissibility condition. I mean, if all you wanted to do was keep your length variables small, then something like lattice Landau gauge would do the same thing.
But so here point is, so this kind of admissibility condition is gauge invariant condition because this is the bracket. So under the gauge transformation, so same unitary matrix appears on left and right side. Yeah, but so here, so I want to make every step manifestly gauge invariant. So within this formalism, we do not perform any gauge fixing. Yeah.
This the field is like external field. I mean, it's not dynamical or.
Yeah, so here it is treated as non-dynamical. Yeah, non-dynamical. But yeah, but you can sum up this B field with satisfying this constraint, then you can define a PSU and gauge field.
What's this construction or, you know?
No. Here we just pick up a specific configuration of B field satisfying this constraint. Yeah.
Yeah, no, because you also put dynamical part as well, right? So
yeah, so this SUN part is completely dynamical. Yeah.
When you constructed your theta should be by 2 pi, what about, you know, as function of theta? You also can construct for any theta.
So what we have defined is this topological charge. So yeah. So we can now define this topological charge with background B as a path integral of this link variable, but it's now restricted to this admissible configuration. And just consider S Wilson plus I theta Q topological, and this Q topological is that Q topological. Yeah. So now Yamil theory at any theta is defined in this way on a lattice. Yeah. Exactly, right. Yeah, right. Exactly. Right. Yeah, so for example, you can perform gradient flow. So if gradient flow is now done with this Wilson action coupled with B field, then gradient flow gives a good continuum configuration under the presence of B field. And indeed, so if that kind of classical approximation works well, then this Q top is really F tilde, where this F and F tilde is given by this exponential phase of this U tilde bracket variable. Yeah. So if in the naive classical continuum limit, this topological charge is same with FF tilde. So if you have a nice gradient flow to achieve that nice classical configuration out of lattice field, then you can compute it in a naive way. Yeah. Here, no. Yeah, but for example, having a boundary, so change of the topological sector is more easily done. So for example, yeah, as a process of the Monte Carlo hybrid Monte Carlo update, it's possible that we can take open boundary and just making closed boundary, closing the boundary and sampling it. So that gives makes the barrier of topological sector much less. Yeah. I'm interested in, but currently I have no idea about.
He constructed also a definition of the
Mm-hmm.
from adjoint silence current
I see. Yes. Right, right. So under the gradient flow smearing process, it should be ensures that this kind of admissibility condition should not be violated. Yeah. But the point is, as long as gradient flow is keeps this admissibility condition is intact, topological charge does not change. So if gradient flow violates this condition at some stage, then topological charge becomes ambiguous. Yeah. So if you perform smearing too much, then at some step this condition should be violated. Yeah. So you have to be careful that this condition should not be violated at any smearing step.
I didn't understand it. You already said that direction, but you could also try to define the topological charge by
Overlap fermion, right.
I mean, this was meant.
Yeah, right. And the index, right. That's
So
exactly. But even in fundamental case, so overlap definition of topological charge and this geometric definition of topological, so connection between them is not yet so clear at finite lattice spacing. Yeah. And indeed, it's one of the important program of constructing chiral gauge theory. Yeah, we have to know much data about the local cohomology of lattice gauge field to construct chiral gauge theory. Yeah, and that is one of the big problem inside it. Yeah. Yeah, thank you so much.
Can you hear me now? Good. It's a pleasure to be here, not only scientifically. I'm really glad to see all the friends that I've missed for some time, old and new. And yeah, I basically last year in continuous advances, I gave a talk about with a similar title, except it was in 3 dimensions. I'm going to talk about 4 dimensions now, and I'm going to correct some things in 3 dimensions. So basically, you know, it will give some hints about what phase in 3 dimension is. The talk is with these 2 gentlemen. Nakarin is a postdoc at Durham, and Mohammed is another faculty. Well, this is, I wanted to comment, you know, if you're going to collaborate with me, you better make sure that the Google results returns good pictures of you, because I take the first ones. So, yeah, so let me plunge into it and immediately review what kind of prerequisites of this thing. What I'm going to consider is SU and Young-Mills theory coupled to both adjoint and fundamental matter. But my starting point will be the super Young-Mills theory, which just has adjoint one while flavor of adjoint matter. And I'm going to keep only one while flavor, not going to. In fact, for the purpose of this talk, I'm only going to add one fundamental just to make it simple. Most of the interesting things that I want to discuss happen here. But first, let's review the one adjoint while fermion. This theory is supersymmetric, and it's known to have well, it has two important symmetries. One is the discrete chiral symmetry, which rotates the phase of the while fermion. And the other one is because this is adjoint representation. There's a one-form symmetry under which fundamental Wilson loops transform as a phase. The phase of this theory breaks the discrete chiral symmetry spontaneously by the development of the condensate, much like in QCD, except the chiral symmetry here is discrete. And because it's discrete, it has n vacua, which can be labeled by this integer here, by this phase here, which is nth root of unity. So since vacua are discrete, we can take 2 vacua, vacuum labeled by k and vacuum labeled by k prime, and they must be separated by some kind of a domain wall, which you can label with n, which is the difference between these two integers. Now, this domain wall was conjectured to be dual to super Young-Mills theory in 3D with some Chern-Simons level related to this n here, and by these gentlemen here. And that theory was analyzed. That theory and related theories were analyzed by Zohar and his collaborators, and conjectured to be a TQFT in a TQFT phase of this type. So my interest, actually, this is the connection with the last year's talk in 3D, is that we're going to modify the theory in the bulk and also make this assumption that there's a relation to some theories of the kind in 3D and see what 3D phases exist. But of course, that was my original interest of looking at 4D, but we will also have to understand the phase diagram of the theory in the bulk. So now what we're going to do is we're going to take this super Young-Mills theory and we're going to add massive fundamental matter, which is not going to be a supersymmetric multiplet. So we're going to break supersymmetry explicitly. We're going to add massive either one flavor of fermion or boson, but again, for the purpose of this talk, I'm going to just focus on the fermion. The boson has also an interesting story, but I won't have time for it. So the question I want to ask is what happens as mass m is reduced, and in particular, what happens in the bulk and what happens on the domain walls. When mass is very large, of course, nothing will happen. You can just integrate out massive matter, but when you reach the scale of lambda QCD, then something could happen, and this is what I want to understand. And I'm going to make a connection with 3D here by assuming, as you will see, there's still going to be some domain walls, and in particular, you know, when domain walls are when mass is very large, the theory in the bulk has massive fundamental matter, and it was conjectured to be super Young-Mills with some particular Chern-Simons level. And yeah, sure, but I'm looking at low energy dynamics. I'm looking whether there's a phase transition. Okay. You mean on the domain wall, or? That's correct. There's going to be actually some change on the domain wall immediately. There's the domain walls actually spontaneously break supersymmetry, and there's a Goldstino on the domain wall, which I expect to be lifted immediately. But yeah, the TQFT though should be robust, right? You cannot just lift it immediately. But you're right, yes. So I'm going to conjecture that the theory on the domain wall, at least for very massive matter, is again super Young-Mills in 3D with some fundamentals added to it. And that was exactly the theory I was talking about last year, if you happen to. Yes. Well, no. Well, that will be changed somehow in the theory with fundamental matter. Well, I mean, it depends on how you probably want to match so that when you integrate them out, the level is that of but yeah. Mostly I will focus on T preserving domain wall, because the talk of last year, if you remember, was about T preserving 3D theories. So I will pick the level so that it's T. Well, if you remember, I don't know, you probably don't remember. Yes. Yes. There was also a conjecture of it's closely related. That's right. These are more modern, refined conjectures. Let's say. Okay, so what are the symmetries? And the symmetries, so as I said, the theory is either supplemented with a boson or a fermion. I'm going to focus on this case. And the symmetries now, there's no one-form symmetry because I broke it explicitly with the fundamental matter. But instead, there's a baryon symmetry, which rotates the phase of either the fermion or the boson. And notice that the way I normalized this, I normalized it with the parameter alpha so that alpha is 2 pi periodic up to gauge transformation. Because when alpha is 2 pi, this is a pure Zn phase, and that's a gauge transformation. That's not a global transformation. This turns out to be important. And in fact, a consequence of this is that there will be a mixed anomaly between U1 baryon and Z2n chiral. Yeah. Well, when this is pi, this is not a fermion number. it would have to be something like n times pi for that to be the case. But
No, of course. No, but I mean, you said that we're going back after 2 pi there, and I'm trying to say that we're going back after pi there.
After pi n, it's still a global symmetry, but cannot be spontaneously. Well, it could be a global symmetry or not, depending on whether n is even or odd. But yeah. Of course, yeah. There are two kinds of theories. But now the way I'm going to approach this is actually to go to the massless limit, because there's actually more symmetries in that case. In that case, there is a non-anomalous U1 chiral, which rotates the phase of the fundamental and of the fundamental and of the adjoint in such a way that there is no anomaly. Okay, you can cancel the anomalous contributions of the two fermions and form a U1 chiral symmetry, which is exact now quantum mechanically. And in fact, there's a whole bunch of triangle anomalies here. There's a pure chiral anomaly, U1 chiral anomaly with this coefficient here. This coefficient you just get from sum of the cubes of the charges of the adjoints and of the fundamentals. There's n squared minus 1 adjoint and n fundamentals. There is a mixed U1 chiral U1 baryon, and it was crucial to get these are baryon gauge fields, which have to be properly quantized, and it was crucial to take into account that this alpha parameter was defined as I defined it, that it changes up to a Z2 phase. It will actually, putting these baryon fluxes will give you kind of a fractional color fluxes. There's going to be intertwining in the two. But if you do everything correctly, you get this. And then there's a mixed gravitational anomaly. This is the first Pontryagin class of the tangent bundle. There's a mixed gravitational anomaly with the chiral symmetry. Yes, exactly. So under discrete chiral symmetry, this is just, if you put alpha to be 2 pi over n, this just does not transform at all. Only this transforms. So it's a subgroup of the U1 chiral. Yeah, in the boson case, it won't be the case, but something else. Actually, if you condense the boson, let me just say this. If you condense the bosons completely, you get the fermionic theory. You Higgs one part of the gauge group, and you get a one fundamental fermion, and so you reduce it to this case. So it's can be reduced. Now, when you actually add a mass and you break this U1 chiral symmetry down to Z2n chiral, all of these anomalies actually remain. None of them, something remains, okay? This one was studied in a paper by, I don't know how to pronounce this name. Can somebody help me? In 2018, but also by Zohar with his usual suspects, some of the usual suspects, that even though you break the U1 chiral symmetry down, something remains. These two terms are related to some, if you wish to think of it as a Zn cubed triangle anomaly, but also this anomaly remains. And you can see it kind of by reducing this thing to a Zn gauge field. You can still not remove it. This is like a 5-dimensional inflow action, and you can see it in more detail. But the point is that all of these anomalies still remain even when you add this. Yes, this person did that. Yeah, it's the same. It's the same. I think it's the same. Yeah. So you can rigorously show this, or no, I can't, but there are people who can, who claim that they can, and I believe them. My point is that all of these anomalies are still there in some shape or form. And therefore, the most natural, you see, all of them involve the chiral symmetry. And therefore, the most natural way to saturate all of them is just to break spontaneously chiral symmetry. In fact, this is a chiral symmetry and gravitational anomaly, so you can't really saturate. You could I'll consider one more case where you can saturate, how you can saturate them. But the most natural way to saturate them is just to break this discrete chiral symmetry throughout. And at the end, when mass is exactly 0, you just have a U1 symmetry, which is spontaneously broken down to Z2. So you have an exactly massless Goldstone boson here. However, there is an a priori alternative, and the alternative is with composite fermions at this massless point. And there is a choice of charges for these composites, which will do the trick. Okay, I here just outlined the choice actually relies on the fact that the cubes of these charges of the would-be composite fermions of the chiral charges has to have this this index here, exactly like here. It has to add up to this thing, and then you note the identity that this thing actually gives you the sum of i's from 1 to n gives you the most important piece, and then you just need one more charge, which is the Q0 charge, which is -1. It's given here. So the rest of the charges are just -2i plus 1, and then you have to assign baryon charges to satisfy this, which means only 2 of these fermions have baryon charges which are opposite, and then everything is satisfied, the gravitational anomaly and everything is satisfied. So this is one potential a priori option. But that option is actually excluded by a type of Vafa-Witten theorem considered by Weingarten around the same time, where he proved in QCD, but the proof goes throughout. It only uses actually correlators of fundamental fermions and positive definiteness of the measure to prove that any baryon is heavier than a meson. And so if a baryon is massless, then a meson should be massless, but the only way a scalar should be massless naturally is if it's a Goldstone boson. So a massless baryon would imply a Goldstone boson, but then, you know, it kind of is not naturally, yes. Adjoint is always massless, yes. Yes, we checked it. Yeah, we checked it. Yeah. Yeah. It is positive. You mean on the lattice? On the lattice, you have all kinds. So, for example, actually, in Weingarten considered the theory on the lattice, and on the lattice, he couldn't prove this identity. He had to prove a slightly weaker identity because the Wilson Dirac operator did not have this positive definiteness always. So he had to assume that there's a certain number of flavors and so on. But in the continuum, at least as a formal proof, this works. And the Pfaffian of the wild fermions. We were very confused. Actually, I learned about this from David Tong, and he said it for a very similar theory. And I asked him, "Are you sure this is positive definite?" And then me and Nakarin sat down and worked it out. No, on the lattice, yes. In the continuum, it's a formal proof. In the continuum, you can define this as positive definite. Yes. You can get away from the sign. Okay. So, yeah. In the continuum, certainly the sign is not, at least formally. Now, if you regulate it with polyvirars or something. So, so this is excluded. And U1 chiral symmetry is naturally just spontaneously broken. So this is the phase. But there's still a question of how it saturates all the anomalies. Because if you just consider a Goldstone boson in the infrared, it doesn't really saturate formally anomalies. And this bothered us for some time. And then when we realized that there are these fermions which saturates anomalies, we just realized we can gap them out in a symmetric way just by coupling to the Goldstone boson. So they're massive, but I like to keep them in just because you saturate the anomaly. But their true purpose is that they will actually show up as massless on vortices in this Goldstone boson phase. So this mass term is not well defined at the vortex, and it kind of vanishes at the vortex, and this is where you will see the fermions. But so this, here, yes. So these two are charged under the chiral symmetry, right? So the mass term, without the Goldstone boson, you cannot write this mass term because it's charged under chiral symmetry. But now you have a light degrees of freedom, the Goldstone boson, which can soak up the transformation of this mass term. And so it's a well-defined mass term which gaps out your fermions, and these fermions saturate all the anomalies. So you can't write the Wessel-Minowitten term. That's the problem. For a U1, how do you write the Wessel-Minowitten term? It's just a U1 Goldstone boson. All of them. So phi f wedge. Well, yeah, but that's when you gauge it. But when you put background fields, yes, that's the anomaly. Okay, maybe you're fine with that, but I wanted to see what degrees of freedom are there. In fact, one of my biggest concerns was I'm going to look at domain walls here, and I was worried that maybe domain walls have some degrees of freedom on them. Yeah. Yeah. That's going to reproduce it, right? But these fermions should match that anomaly by construction. Yes. No, these are the meson. What I mean by meson are insertions of fundamental. This is what what Weingarten proved was only for fundamental matter. So what he considered a meson were just insertions of fundamental fields. And the point is that if you have a baryon, which is carries n insertions of fundamental field, you can show that it has a larger mass than a meson, which is just two insertions of the fundamental. Yes. How am I doing on time? Okay, here I inserted now what I want to do is I want to go to the massive limit in this effective theory. The effective theory I wrote down has a massless Goldstone boson, but and U1 symmetry, which is spontaneously broken. I now want to break it explicitly down to Zn by inserting some mass term for the fundamental Dirac, which is something like this plus its complex conjugate, and that is proportional to this operator in the effective theory. And as you see, it induces a cosine n phi term, which leaves n degenerate vacua. And for completeness, I'm also going to insert a mass of the adjoint, and the mass of the adjoint would couple like this. It's the adjoint's modulus is related to the theta angle. You can put all the theta angle dependence. Now the theta angle becomes physical because both fermions are gapped, and the theta angle can be put in the phase, and it generates this cosine phi plus theta over n term. And generically, for generic value of theta, only one true vacuum remains. But if you dial theta to some particular value, and if the masses if the mass of the adjoint is sufficiently large in its modulus and theta is equal to pi, then you will have two degenerate vacuum, just like in pure Yang-Mills theory at theta equal pi. So, oh, sorry, this was, so the phase diagram looks something like this. If you plot the phase diagram as a mass and mass of the adjoint to the power of n, so that this is the theta equal pi, basically, when this object is negative, this is theta equal pi. Then you have this phase diagram where Zn chiral is spontaneously broken to Z2 here, and there are n vacua. If you go upwards with mass of the adjoints, then you just trivially gap over, you have just one vacuum. But if you go down and mass of the fundamentals is sufficiently large, you are in the T broken phase, you have two degenerate vacua. Two of these vacua still remain. And at the end, there's a massless pseudoscalar, which Zohar contributed to this. This is the QCD, basically, at theta equal pi with one flavor. Well, one fundamental favor, and they already pointed out that there's this massless pseudoscalar, which actually becomes this massless Goldstone boson at when adjoint fermions are massless. So, are there any questions about the bulk? Oh, in plotting, we weren't careful about the shape, but yes, you can. You can in principle, but because this is m to the n, it would be okay. So we didn't bother. It's linear, I think, in M adjoint. If this was m root of this thing, then this would be a line. So are there any questions at this point before I continue to the domain wall? No. Yeah. Okay. Not the question. Timestamp. Okay, so now I want to go back to the massless adjoint case and ask about what are the domain walls. And now the domain walls in this theory are actually kinks, okay, which interpolate from, for example, phi equal to 0 to phi 2 pi over n. And what do we know about them in this small mass, fundamental mass regime? Well, they do not carry any fermion zero modes. You know, when we put these massive fermion zero modes, a priori, I thought maybe this is why I worried about these anomalies. I thought maybe, although there's no anomaly reason for domain walls to carry them, at least not all of them, some of them may, none of them carry any fermion zero modes, and therefore they're trivially gapped. This is unlike the large mass where there was a TQFT. So that already indicates there's a phase transition. The domain walls also, the domain wall, for example, from here to here, repels from the domain wall from here to here. So the composite domain wall from here to here is actually unstable. They repel, it decays. This is again unlike in super Yang-Mills where there are composite domain walls. So there must be a phase transition. So that's statement number one. This 3D theory should have a phase transition. Okay. And the phase diagram, actually refined phase diagram, looks like this. Even though there's no transition in the bulk, there is still a phase transition on the domain wall where TQFT gets eradicated in most cases. But there's one domain wall which is special, which actually does have anomaly inflow and cannot be made trivial. And that's the domain wall which goes from here to here. Now, I already said that such domain walls are not stable, but they should correspond to, they are stable actually in super Yang-Mills. And they are T-preserving because T-symmetry, you can think of T-symmetry as flipping this to this. So the T-symmetry is preserved if I go from this vacuum to this vacuum. And if it really bothers you that in my effective theory this is not stable, I can always add some Zn, Z2 and breaking deformation down to Z4 so that I only stabilize these two vacua. Okay, that's always something I can do. And I'm going to make a claim that this is somehow related to the 3D theory, which are T-preserving. And these cannot be trivial. And indeed, they are not trivial because if you lift these vacua here now, the only way, just with a small deformation, the only way you can go from here to here is either going this way or going this way, which means there are two states. And it means that the domain wall theory breaks spontaneously T symmetry. There is actually a mixed TU1 baryon anomaly inflow on this domain wall, and this is consistent with that. And last year, if you remember, I was mostly trying to saturate, if those who were looking at my talk last year, I was mostly trying to saturate this anomaly by massless composites on the domain wall. But it turns out that T symmetry, and I said you can also saturate it by breaking T symmetry, but then my talk would have been over way faster. So you could, but that's not what happens here. Maybe you could. I mean, in principle, it's matched by TQFT when fermions are very large. And we were conjecturing that that TQFT gets destroyed. No, but there's T-preserving TQFTs. But let me just, in the last minutes, also make a kind of a stretch of the imagination conjecture that perhaps there may be two-phase transitions on some domain walls, especially for low n. And the reason why I think that may be possible is that this is the massless case, and there's a kind of Mexican hat. When you add this deformation, these are shallow vacua, and that's why you have T-symmetry breaking. You're kind of surfing along this valley. But if you take the mass of the order of lambda, if you stretch this picture, then there's just one scale. And in the origin of this potential for some condensing scalar, order parameter of your spontaneous breaking, there may still be some trajectory which takes you through the origin where there should be massless fermions. So it's not inconceivable, especially in SU2 case, where for a one scale potential, this is kind of pair of pants is the most natural potential that you go through the origin and you have free fermions. So three phases are not completely excluded, but most likely for sufficiently large n, you just have two phases on the domain. Yeah. So I think for SU2, probably there may be an intermediate phase. But you see, for SU2, when mass is very small, this is Mexican hat with two minima here. So you still don't have a one scale potential. But maybe in some intermediate regime, you do have going through the origin where there would be fermions. Okay, so my conclusion is more or less what I said so far. So these anomalies seem to completely constrain the bulk phase diagram. The Weingarten Waffa-Witten theorems exclude massless composites in the bulk. Z2n chiral symmetry is naturally spontaneously broken, just like in super young Mills, but still there is some transition. This is a different phase. It has a different kind of domain wall in some sense, not in terms of low energy bulk excitations, but domain walls have different excitations. Now, T-preserving domain walls break T-symmetry spontaneously, and I think this is good evidence to indicate that QCD3 with this matter content also has a transition in TQFT turns into T-broken phase, at least for small enough mass. But there's a possibility of intermediate composite domain wall phase, especially for SU2. And there's a generalization for multi-flavors, but most of the essential ingredients are. So with that, I'd like to thank you for listening.
So there is no
fermions of the fundamental domain modes, but the fundamental vortex are still not fermions.
Yes. Yes, because of this potential, right? I mean, if you look at this potential and you take a vortex, somewhere in the middle of the vortex, you have to you go through the origin. So the origin. Yes. Yes.
The wrong one.
Yeah. The wrong anomaly. Right?
Like the one without set of fermions.
Yes. Yes. Yeah, yeah. So this is exactly. So you can think of these fermions as candidates for the vortex. Fermions, yes. Yes. Right. Yes, that's a very good question. So the difference there is that when mass goes to 0, then there's a runaway potential for one flame. Yeah, small mass, yes. But it's a very good question. I have not studied that in detail. Is it? Mm-hmm. I see.
In so you know in detail there. I mean,
Mhm.
you stop run away and
Right.
Yeah, and you know
They were able to study for all values of mass, including intermediate.
Right.
And they did indeed find a 3D theory with multiple things,
Okay.
including intermediate.
Very good. Yeah.
So either break for symmetry a little bit, find some evidence for the theory.
Very good. Yeah. Thank you. That was Benini, you said? Well, I think it's an IR duality kind of. It has the same anomalies, the same. Yeah. It's an IR duality. If you wish, it's effectively theta angle pi. Oh, it's the same. You can rotate the phase into one or the other. This is by using a non-anomalous chiral symmetry rotation. Remember, there's a non-anomalous chiral symmetry rotation when masses are 0, which turns into just shuffling the phase for the. So the T preserving the main wall is only for n even. That's correct. Yes, but for the bulk phase is the same. So there's no anomaly inflow on any of the domain walls when n is odd. So they're all probably trivial. I mean, they're trivial for small mass, but maybe for, I don't know what happens intermediate. There's a TQFT on them until lambda QCD.
more questions.
Maybe I should say one more thing about T preserving TQFT. This is what we studied. There's a Goldstino there, and interestingly enough, on it, it cannot be lifted because there's a pure T anomaly which protects it. So it will get lifted only when TQFT is destroyed because the three conspire to match the anomaly, which Zohar and company discovered. But even when you add fundamental matter, you cannot lift it, even though you broke supersymmetry, which is kind of interesting because. Excellent, yeah. This was one question that I wanted to ask because.
How did I turn this off?
All right, is this okay? Okay, yeah, that's right.
Starts, our next speaker is Matt Walters. I included
Perfect. Thank you. First off, I just wanted to thank Alexei, Andreas, and Igor for putting together such an excellent workshop. I've really enjoyed all of the talks, and I'm really grateful for the opportunity to be here and get to know many of you. So I come from the kind of more bootstrap side of things, but for a while now, I've been working on kind of developing kind of a general method or a general framework for trying to use data that we can get from fixed points, so the sort of things that we can obtain with the conformal bootstrap, and try to figure out how to use that data to study deformations of conformal field theories and apply it to more general like quantum field theories. And so this work has been done with various linear combinations of great collaborators. I just wanted to take this opportunity to give a particular shout out to my junior collaborators, Yuan Sin, who's here and is currently a postdoc at Yale and will be moving to Carnegie Mellon in the fall. Brian Henning, who's a postdoc at EPFL and will be moving to Santa Barbara in the fall. And then Jed Thompson, who actually just defended his thesis at Stanford and will be moving to a postdoc at Johns Hopkins and University of Maryland. And so kind of to be maximally ambitious, the kind of goal, the long-term overarching goal that we have is we really want to try to develop a general method or a general framework that we can use to really compute dynamical observables. We really want to study real-time physics. So everything here is going to be formulated directly in Lorentzian signature. And we want to be able to apply this method in general strongly coupled QFTs. And so really I want to, the goal would be to where you name a theory and you name an observable, and we want to try to figure out kind of how to compute it. And so like we don't just want to talk about the spectrum, we really want to talk about quantities like the wave functions, so like parton distribution functions or time-dependent correlation functions, both in the vacuum or excited states, but also at finite temperature or finite density. Things like scattering amplitudes, or you name it. So you tell me kind of what you would like to see, and I would like to push towards having the framework kind of this well oiled to where we could really try to shoot for this over the long term. So kind of, to be completely honest, kind of my big dream or my goal is to try to compute something like E plus E minus. So to really try to compute something like this that is clearly inherently non-perturbative, very dynamical, and to try to compute this kind of from first principles. So this is the goal. Yes. No, good. So good. So I think that kind of this goal is very complementary to the lattice. Like I think that the sort of observables that we're kind of naturally able to target are precisely those where the lattice has difficulty, and vice versa. So I think this is viewed as a very nice kind of complement in our arsenal, another tool in our arsenal. Okay, so good. So we're very clearly not there yet, but I think we've made some like very exciting, very concrete kind of first steps. And so given the audience today, I'm kind of going to give more of an overview, but I'm happy to discuss offline kind of more details, both about the method or particular observables or theories that we've studied so far and kind of where we're going. So here are kind of two concrete examples just to give you a flavor of the sorts of things we've been thinking about. So for example, in the 2+1D ON model, we've computed the total cross-section, for example, as a function of the center of mass energy. And so here we're looking at the large N limits, but still at finite coupling. So this is an inherently non-perturbative calculation. And what's nice about the large N limit is just that we have something to compare to. So we can really kind of test the method. And so we can resum the set of bubble diagrams, and that gives us the magenta line, which is kind of the theory prediction. And then we can use the method I'm about to tell you about for computing this numerically. And we see that we agree to within kind of percent level accuracy. And this is with minimal effort. So this is a basis, which I'll explain what this means in just a second. But basically, I have to diagonalize a 6,000 by 6,000 matrix. And the construction and diagonalization of which takes roughly the order of 10 seconds. And this is computed on a laptop in Mathematica. But the advantage is that the method that I'm going to describe doesn't rely on large N at any point. So we can also do this at finite N, and actually we're pushing to do this right now to try to study, say, 1 plus 1D and 2 plus 1D phi to the fourth, or more generally ON models, and push beyond that. But we're not just looking at scattering, we're looking at other things, like, for example, the survival probability. So just kind of the evolution of some state. So if I prepare some, say, initial wave function, and then I evolve it in time, kind of what's the probability of measuring the same state at some later time. And so here I'm looking at the 1 plus 1D phi to the fourth theory. And what I've done is I've taken kind of a random state with some energy density, with some kind of expectation of the Hamiltonian. I've chosen of the order, like roughly 20 states, 20 randomly selected states, and then just kind of evaluate their evolution in time, and then average them. And what we find is that those results are in excellent agreement with kind of predictions of random matrix theory. So this is kind of a very analogous type structure to the spectral form factor, something that's been studied a lot in kind of chaotic systems recently. And it's got kind of the same similar dip ramp plateau, just the dip is a bit kind of more shallow. So here we're able to see that we're really accurately producing kind of the evolution of states for even very high energy states as well. And so this was a little bit more computationally intensive, but still we're talking computations on the order of an hour on a laptop. So I really want to stress we are not sophisticated numerical people. So I think there's a lot of room to grow in this direction, but right now kind of our focus has been on kind of just more conceptual questions and trying to understand the method of how do I use conformal field theory data to generate plots like this in more general theories. And so how are we doing this? So the kind of approach I'm going to describe has the incredibly catchy name of conformal truncation. And the basic idea is the following. We kind of rely on this modern picture of quantum field theory as renormalization group flows between fixed points. And so if I take a generic theory, most theories systems that I care about have some finite set of mass scales, say like lambda QCD or things like this. And if I go to very short to very long distances, so I go far away from these mass scales, the system typically becomes scale invariant and approaches some fixed point. And so, for example, if I go to very short distances, I can describe my quantum field theory as coming from some UV fixed point, some short distance conformal field theory. And this picture is very suggestive. Somehow, all of the physics contained along this RG flow must somehow be buried within the UV fixed point. Somehow nature knows, given some initial starting point, what's going to happen all along the flow. And so the question is basically, is there a way for us to extract kind of some subset of the IR information from this UV data? And so the kind of input that I'm going to be using is the natural kind of data of the conformal field theory. So things like scaling dimensions of local operators or operator product expansion coefficients, kind of connecting them together, describing the dynamics. So this is going to be the input. And then the goal is to try to obtain kind of physics that most people care about, things like the spectrum of bound states, or things like correlation functions, time-dependent correlation functions, or scattering amplitudes, or you name it. Or to kind of say things more simply, conformal truncation is just a means of laundering results from one Simon's collaboration to another. So, great, this is all well and good, but how do we do this? Like, this is a very suggestive picture of CFTs somehow know information about more general quantum field theories, but how can we extract this data? And so kind of the approach we're going to take is a very old-fashioned one in some sense, kind of the most naive one, which is that if you want to study dynamics in a quantum mechanical world, that just means diagonalizing the Hamiltonian. So the generator of time translations is the operator that controls the dynamics. And if you take a very bright undergrad who hasn't yet taken QFT and you try to describe it to them, they would exactly say like, okay, great, I have some new degrees of freedom, I have Lorentz invariance, but solving a theory means diagonalizing the Hamiltonian. But of course, the moment you take a QFT class, you're immediately told, forget all about Hamiltonians. We're never going to talk about that ever again. And the reason is very simple, right? At weak coupling, diagonalizing the Hamiltonian is incredibly impractical. If you even take a free massive theory and shift the mass, you have to resum an infinite set of contributions. And just doing old-fashioned perturbation theory is very impractical. And we reorganize calculations in a way that makes Lorentz invariance manifest, and that leads to Feynman diagram. And at strong coupling, this is impossible. I have a continuously infinite Hilbert space. I have no idea how to even begin thinking about diagonalizing this Hamiltonian. Yes. Good. Good, but okay, good. But in a QFT, like in a lattice system, yes, I can try to do something like this of diagonalize the Hamiltonian. But I'm saying in an infinite volume continuum quantum field theory, I have no idea how to do this. And so what we're going to do is we're going to be a bit less ambitious, and we're just going to say, okay, fine, let's diagonalize part of the Hamiltonian. And so the kind of basic picture is this kind of general method known as Hamiltonian truncation. And it's a very old idea in non-relativistic quantum mechanics called the Rayleigh-Ritz method. And it's a method for approximating the low energy eigenstates of a Hamiltonian. And the idea is incredibly simple. So there's basically just 3 steps. One, in the example of a QFT, where you have kind of a continuous Hilbert space, you need some way of discretizing it. I want to put this on a computer. And so I need some way of having a discrete set of basis states, of energy eigenstates. And so the kind of typical way people discretize this is to say, go to finite volume. But any sort of kind of discretization is going to work. We're going to talk about something different in the method I'm going to present today. Then once you have a discrete Hilbert space, then what you do is you truncate. So you just say, I'm going to restrict myself to some finite dimensional subspace of this full infinite dimensional Hilbert space. And so if you look at the Hamiltonian is some infinite dimensional matrix. And so we're just going to restrict ourselves to some finite dimensional subspace, evaluate the Hamiltonian within that subspace, and then forget about everybody else, pretend that this finite dimensional matrix is the Hamiltonian, and diagonalize it. And then the idea is that the eigenstates of this kind of truncated matrix are an approximation to the energy eigenstates of the true full infinite dimensional Hamiltonian. And so the kind of basic idea, the kind of way you formulate this approach is you take your Hamiltonian, you split it up into 2 parts, a solvable piece H0, and then a deformation V. And even though this looks insanely perturbative, this looks very reminiscent of perturbation theory, I'm not assuming that V is a small perturbation. The reason I'm splitting it up this way is that H0 gives me a basis that I can use to compute the matrix elements of the Hamiltonian. I just need some theory where I know how to compute the matrix elements that go into this. And then once I have the matrix elements, I forget all about H0, and then I just diagonalize. Okay? So what's nice about kind of this Hamiltonian truncation type method is it just kind of rephrases the question to what's a good basis. So in other words, where do low energy eigenstates live within the Hilbert space? Like what's a good subset of the Hilbert space that I can restrict myself to that will efficiently kind of capture low energy? And there are various methods that you can do. This is a very old idea, like where there was a lot of pioneering work kind of in the 80s in taking the guise of like DLCQ or the truncated conformal space approach. And then there's been kind of a nice resurgence of interest in this in using various choices of basis, choices of discretization, things like this. So the one I'm going to present today kind of takes the CFT picture or this fixed point picture maximally seriously and says, okay, great. I'm going to think of my QFT as some conformal field theory plus some deformation, some set of relevant operators. And so I'm just going to use kind of the natural basis from this UV's fixed point. So that's going to be the basis that I use. And so going through the checklist of general truncation methods. So first we have to discretize. And so we're going to use the CFT basis of local operators. That's kind of the natural objects in a conformal field theory. And so the kind of spectrum of operators is discrete. But for each operator, we have a continuum of states. So what we're going to do is we're interested in systems that preserve translation invariance. And so to kind of make maximal use of this, we're going to go to Fourier to momentum space. And so we can think of these objects as kind of CFT partial waves. So it's a continuous family of energy eigenstates labeled by individual local operators in the conformal field theory, which are labeled by their scaling dimensions and whatever other quantum numbers. And so to make this basis discrete, we need to, for each operator O, discretize kind of the continuous range of energy states that we get out. What we're going to do is we're going to discretize them into just discrete bins, but you could choose whatever discretization you want. And so then we have a discrete basis, discrete set of operators. For each operator, we have a discrete set of kind of energy eigenstates where we just discretize this parameter E in the Fourier transform. Then we need to truncate. And to truncate, we're going to do 2 things. One, we're going to restrict ourselves to a finite number of operators. So we're specifically going to keep operators with low scaling dimension. So we're going to set some threshold, some cutoff delta max, and only keep states below that. And then for each operator, we keep a finite number of energy bins. Then, once we have that basis, we can construct the Hamiltonian from the conformal field theory data. So the Hamiltonian matrix elements look like this. The Hamiltonian is just an integral of a local operator. It's just the deformations that I'm adding to my CFT. My basis states are built from local operators. So this is nothing other than just a conformal field theory 3-point function, which is completely fixed by the scaling dimensions and OP coefficients of the CFT, which is exactly the data that we get from the bootstrap. Yes.
Dilatation or dilation is epiconductorial, right?
So good.
Because I mean your type of calculated by delta, right? So then you're like not Hamiltonian, but you know this.
No, good. Okay, good. So I want to be maximally clear. So what we're going to do is our states are defined on the plane. So we're not working on the cylinder. And so our Hamiltonian that we're going to diagonalize is really the generator of time translations, not the dilatation operator. We're just organizing kind of our basis. We're keeping them by kind of conformal Casimir eigenstates. Like that's what we, yeah. We're using dilatation. We're using no. Well, maybe I'm not understanding your question, but just to stress, the operator we're going to diagonalize at the end of the day is just the Hamiltonian. We're using kind of eigenstates of the dilatation operator as a way of kind of organizing our basis, if that's like if that makes sense. Okay, good. So then we given a CFT, so I'm going to take that as my given input. I want to consider a particular deformation. I construct my basis, I construct the Hamiltonian, and then I diagonalize. And what do the results look like? Well, the first thing I get is I get kind of the mass spectrum, just the spectrum of mass eigenvalues. And so in the true continuum QFT, I expect something like this. I have the ground state, the vacuum. I might have one or more excited, like bound states. And then I have kind of the multi-particle continuum. What our data is going to look like, because we've discretized the kind of Hilbert space and used a finite size basis, we're still going to find the ground state. We're still going to find some approximations of the excited states, and then we're going to have some dense discrete spectrum of states corresponding to multi-particle states. How do I actually evaluate them? So yeah. That's right, exactly. So yes, that's right. Yeah. Ah, good. So yeah, so for a generic, so depending on the scaling dimension of your relevant operator, there will be IR divergences. And what you'll find is the following, is that so let's say I just put in some IR regulator for now. So I have some, functional momenta that diverges with the IR regulator. And then as I take the regulator to like my R to infinity or epsilon to 0, however you want to say it, what I find is that in the Hilbert space, like in the eigenstates, some fraction of the states will diverge and some fraction of the states will be finite. And so basically what these IR divergences do is they just kind of tell you that some part of the CFT Hilbert space gets lifted out and has no overlap with kind of low energy states. And so in practice, so you can do this one of two ways. One, you can do it exactly how we did it the first way, which was just naively of doing exactly this and watching the states get lifted out. And then you realize that actually the states that are left over at low energies are just kind of the kernel of kind of the divergent piece of this, which is completely fixed by conformal invariance. And so you can just restrict yourself to that kernel from the beginning. But you're absolutely right. Generically, if the operator is has a scaling dimension that's too low, then you'll have divergences, but that we understand, like what effect that has on the resulting eigenstates. But that's a very good point.
You should have the same mindset of the rate of public expansion,
Mhm.
because it takes this product of operator
Mhm.
as a significant gain, like,
Right.
So it reminds me.
Yeah, good. I mean, so one thing I can say is that kind of the convergence of this basis is precisely motivated by convergence of the OPE, that very roughly in this matrix. So, what determines convergence of this, right? It's the off-diagonal elements mixing what you kept with what you threw away. And what are the states here? So what are these matrix elements? They're matrix elements between very high dimension and very low dimension operators due to your deformation, which is also a low dimension operator. And so these are kind of low, low, high, which are exactly the ones that are suppressed to guarantee convergence of the OPE. Yeah. So yeah, so good. So I was not planning on talking about this, but yeah. So in practice, so what we do is obviously to define a basis, I have to choose a quantization scheme. In practice, what we've been doing for the most part is working in light front quantization, but that's not crucial to, like, you can formulate everything I'm saying also in equal time. And in fact, we're pushing on doing exactly this to kind of see the comparisons. Now, light cone seems to have a great many number of advantages, especially if you want to study infinite volume observables, things like the S matrix or stuff like that. But it's not crucial. But yeah. No, I'm not relying on perturbation theory at all. Yeah. Yeah. This is, so basically what you're doing is so every example I'm going to show you today is exactly one where the UV is free, just because those are fixed points where we have the most data to put in as an input. So basically what you're doing is you're not doing perturbation theory. What you're doing is if your UV is well, it doesn't matter if your UV is free, but it's easiest to understand. Basically what we're doing is we're resumming an infinite set of diagrams. So if I look at like the set of diagrams, I'm kind of resumming an infinite set of like subset of those diagrams, where I basically just say like, I'm only going to keep a finite set of intermediate states within these diagrams, but I'm going to resum them to all orders, if that makes sense. So if I took kind of the normal, like, you know, Feynman or old fashioned perturbation, like whatever thing I want, and I'm only going to keep a finite set of intermediate states, but I'm going to keep their contributions to all orders in the coupling. So it's very fundamentally different from conformal, from perturbation theory. And the non-perturbative thing is just coming from the fact that I'm diagonalizing the Hamiltonian. Like it's that numerical diagonalization that's doing kind of this resumming to all orders, if that makes sense. Ah, good. Yeah. So good. So this is one reason why we've been working in light front quantization, is kind of to simplify some of the detailed structure associated with the vacuum, or to not simplify, but to shove it aside. But yeah, so what's going to happen in terms of the convergence is, you're absolutely right. There's kind of two pieces that you have to, which this is true in any Hamiltonian kind of method. Like you're using your basis to reproduce two things, right? One, you're trying to reproduce the vacuum of the new, like of the deformed theory, as well as whatever excitations are on top of it. And so what's been nice about kind of focusing on kind of light front quantization is kind of skirting the former to kind of focus on the excitations, but you're absolutely right that different choices of basis could be more or less kind of efficient for trying to reproduce both the ground state or the excited states. And I do want to stress, like, kind of the main message I want to take home from this is not that this conformal basis is the best possible thing you could be doing. It just seems like a generally kind of robust organizing procedure for the Hilbert space. I guarantee you that there are better choices of bases for particular theories or particular observables, and I think this is a question that's worth exploring more generally. Okay. So to summarize, the basic structure is kind of the inputs are 2- and 3-point functions from a CFT. So if I take those as a given, for example, for free theory, but more generally, if I use the bootstrap or whatever to kind of compute this data, that becomes my input. I then just truncate the spectrum of operators to some finite delta max, diagonalize the truncated Hamiltonian, and then my output is both the eigenvalues, but also the eigenstates, which I can then use to compute things like correlation functions or scattering amplitudes. And so this is kind of a general recipe for using short distance data to get long distance physics. And so we've, for the past few years, basically been applying this to various systems to kind of see how it does. And so mostly we've been focusing on systems in 1+1 and 2+1 dimensions. And so here's just kind of a very quick, probably overwhelming highlight reel. But like, for example, we can look at things at like correlation functions near a critical point. So here we're looking at the 2+1d phi to the 4th theory. And for a critical value of the coupling, the gap closes. And this flows to a fixed point in the same universality class as the 3D Ising model. And so what we can do is we can look at correlation functions near this critical point. And we can see that at short distances, say phi squared, phi to the 4th, and phi to the 6th, look very different. In the UV, they're very different operators. But then at long distances, they all flow to the same operator, the lowest dimension Z2 even operator in the Ising model, which is epsilon. And so we get this kind of universal behavior, and we can match this to the scaling dimension of epsilon in the 3D Ising model. But we don't just have to do position-dependent correlation functions. We can do more general time-dependent by looking at, say, Challen-Lehman spectral densities. And so if we have, say, unstable states, like in Yukawa theory, we can measure kind of Bright-Wigner peaks. We can also compute parton distribution functions. This plot was very generously generated by Xuan a couple hours ago. And I wanted to just kind of reply to Varun's talk yesterday that I think we can compute these parton distribution functions, say, not just for mesons, but also for baryons in 1+1D QCD. We can also measure, say, renormalization group flows by computing the Zamologic of C function. And so here we're taking a particular theory that in the IR flows to the Ising model, and we can read off the central charge. We can also study not just kind of ground state, not just vacuum correlation functions, but we can also look at correlation functions in excited states. And so here in phi to the fourth theory, we're looking at, say, the expectation value of operators like d squared phi squared or d phi to the fourth in high energy states. And what we see is that they're actually, one, we find kind of agreement with ETH that these expectation values are just smooth functions of kind of the expectation value of energy. And not only that, but they're agreeing with their kind of finite temperature predictions. And so in this example, at high temperatures, these two operators, the thermal prediction from the CFT is that their expectation values should be exactly the same with some coefficients that I'm absorbing right now. And we find that at high temperatures, they exactly agree. And even the deviations exactly match kind of the expectation you would get from just like perturbation theory at high temperatures. And we can compute scattering amplitudes as well. So we've been exploring a whole host of different kind of observables and theories, but this is a workshop. Oh, yep. Yes, so yeah, so this is SU3. So good. So what I'm, okay, good. So here I'm looking at, yeah, great. So yeah, let's be hyper concrete. So this is, which Yuan, this is from his work, so he should correct me if I say anything incorrect, but so this is SU3 QCD with a single flavor, but you could do it for more general flavors as well. And so here what I'm looking at is the lowest meson, and there we find that the wave function is overwhelmingly dominated by two parton states, even at finite coupling. If you go to higher states, then they have a large contribution from higher parton states as well. And so you'll get more complicated structure, but it just so happens that this lowest one is very well approximated by two particle states. But we're not making that approximation. We're keeping all particle states up to whatever truncation and delta max we keep. So in this particular, okay, good. I definitely agree with, let me think about this. So for this particular model, for the lowest guy, you can see that there's actually a nice kind of prediction of kind of what the fall off should be near x equals 0 from a Hooft. And what we can see is that even as you add higher particle number, like even as you vary the truncation, this seems like a pretty robust that this prediction for kind of the behavior near x equals 0. Now, I'm not an expert on 2D QCD, so it'd be good to talk about like, you know, what features, or if I look at more like higher excited meson states, kind of if the features look roughly different. But we only just started as of a couple hours ago exploring these PDFs in detail. But this is a good question of kind of what features we should be looking for and things like this. Okay, great. But the obvious elephant in the room is, okay, but I would like to use this method to study, say, 4D QCD, or more general gauge theories in 2+1 and 3+1 dimensions. And so there are kind of two different ways that you could envision using this sort of method for studying something like QCD. And the most obvious one, the most kind of like human readable way of thinking about it would be, okay, great, let's take a theory of free quarks and gluons, and then our deformation is going to be, you know, the gauge interactions, and then we'll flow to QCD. But from a conformal field theory point of view, this is an insane thing to do. This doesn't make any sense. These are not gauge invariant local operators. The only reason the Hamiltonian is gauge invariant is because you've integrated this over all of space. And so if you add any sort of, you know, any sort of regulator, any sort of cutoff, then this generically is going to wreak havoc on gauge invariance. And this is exactly the kind of general problem of studying QCD. But an alternative path that makes much more sense from a conformal field theory point of view is to start from some interacting fixed point. And this fixed point could even be weakly coupled, and in fact should be weakly coupled, because I want to have, well, okay, first let's just talk about the picture and then I'll argue. So for example, if I take, say, a Banks-Sachs fixed point, so let's be maximally concrete. So I'm going to be in 4D, I want to study SU3. And if I take, say, 16 flavors, alpha star is roughly 0.04. So this is a very weakly coupled theory. Then what I could do is I can compute the spectrum of scaling dimensions and the OPE coefficients, either just perturbatively or via the bootstrap or some combination. And then the deformation I'm going to add is just a mass term for all of the matter I don't want. So I can gap out all but, say, 3 of the species of quarks. And this will generate an RG flow, also leading to QCD. And precisely because I want a separation, I don't want the kind of confinement scale to be close to this gap, to this mass scale. I specifically want my UV theory to be perturbative exactly where I can kind of compute the data efficient. And so this has the advantage of I'm adding kind of a relevant deformation. It's inherently gauge invariant. There's no subtleties with cutoffs. And I think this is, and we're currently working to compute this data to try to study something like this, either in 3D or 4D. And I want to stress that this kind of secondary approach works for any gauge theory. You name a gauge theory, and we can just add matter in whatever representations until we find a weakly coupled fixed point. And this includes, say, chiral gauge theories. And so this is kind of a general recipe of using CFD data and trying to study non-perturbatively gauge theories. Yes. Good. So that's a good question. At the moment, I don't see how to do that, but that's a good question. In the sense that, like, right now we're being very operational of just like my basis, I specify some number NF, I construct all operators out of this. Now you can like study things kind of in a 1/NF expansion, for example. But yeah, if you really wanted to study this at, say, NF equals 15.5 or something like that, like, that's a good question. I don't immediately know offhand how you would formulate this. In principle, this might be doable, but I haven't thought too carefully about it. It's a good question. Yeah, that's a good question. I mean, in principle, they should be. I like the one thing I would worry about, and this is purely because I haven't thought about it too carefully. Like, I know that as you vary kind of continuous parameters, like it's not. I haven't thought too carefully about kind of the like unitary or whatever the structure is of kind of these systems at finite at like continuous NF, for the same reason that if I like continuous very D, like I just haven't thought about this. Now people in this room probably have, and maybe you're right that we can construct this matrix as a continuous function of NF and try to study the behavior continuously. That's a good question. I don't see it, but maybe. Yeah. Mm-hmm. Yeah. Good. Okay, good. So you're absolutely right. So one thing that we could think about is like, yeah, great. Okay. If I'm understanding your question / comment correctly, yeah, you're absolutely right. So I definitely want this theory to have a decent amount, to flow for a decent amount. I want to have a decent amount of separation between the masses of the heavy guys that I added in purely to give me kind of a gauge invariant, or like a fixed point in the UV, and my confinement scale. And so you're absolutely right that at intermediate scales, these two ways will look very similarly. And so one thing we could try to do is we could try to like use this method as like this kind of framework as a way of kind of understanding how to, in a simple kind of gauge invariant way, like phrase. I agree. Like, these extra matter that I'm adding is just a means to an end. Like, it's kind of stupid. I add them, I use them to compute data, and then I get rid of them. And so it seems like there probably is some way of kind of phrasing the Hamiltonian without them, but this is kind of the most obvious way that or the most algorithmic way that I know how to do it. But it'd be interesting to try to learn more general lessons about how to never use this kind of stupid intermediate step. Yeah. 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 Mm-hmm.
Throwing away a lot of stuff that's going to be very important when you try to get defined.
Yeah, good. I mean, so yeah, you're absolutely right. I mean, I think what's nice about doing this, or I think what's most compelling about doing this, is that we have no choice but to learn something. we'll learn one of two things, right? We'll either learn that the kind of low dimension operators in this theory have large overlap or are sufficient for understanding confinement, or that it's very crucial that we have kind of high dimension information. And so I think both would be excellent. Obviously, one I'd be happier, but I think this is worth understanding just because it tells me information about kind of the structure of confinement or how confinement is embedded within kind of the UV fixed point. So in practice, what we're doing, so that discretization is kind of hidden, but is not too hard to understand, like in this discretization of energy bins. And so basically, so what we're doing is, so here's what we do with the transverse directions. So I mean, it's no different really. So first we fix a total frame. So we just say, I'm going to work, say, in the transverse momenta equals 0. Then my basis will include operators that have like relative transverse derivatives, but those are just additional operators that I can construct. And so kind of the only discretization that I like, that does most of the discretization for me. And all I have left is kind of one that's just the energy for different operators built from different dimensions, different sets of transverse derivatives acting between, say, if I'm studying from a free field theory. That's right. Yeah. So what's nice about this is that like this seems to play kind of maximally well with kind of Lorentz invariance or preserving as much of it as you can. But yeah, you're absolutely right. I mean, it's worth thinking about other like setups beyond this, and some have been explored. And I think this is a good like general question. Yeah. Okay, I think I'm definitely out of time, but the good news is I'm done. So yeah, so there's a lot of exciting directions I think to pursue. The kind of most pressing, or the one I'm most excited about, is starting from interacting fixed points. So either computing Bank-Stack's data perturbatively or using things like n=4 super Yang-Mills to study flows to gauge theories. So to say get pure Yang-Mills in the planar limit from say n=4 data, to kind of generalize or kind of expand this computation of the S matrix elements to try to study things like bound states, resonances, the kind of full discontinuity structure of the S matrix, to study finite temperature dynamics. Here I showed you 1-point functions, but going to higher point functions, we could study hydrodynamics, see like propagation of sound modes, to kind of study systems at finite chemical potential, compute energy correlation functions, you name it. And so I think kind of as we're pushing, I think this is a perfect audience to kind of, you know, tell us what we should do or what we should think about. So thank you for your time. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Right. Okay. Okay. Yeah. Yeah. Right. Okay, great. No, this is a very good point. I think like definitely as we push, I mean, at each stage, because, you know, we're developing a new method and really trying to follow our nose and see how well it works and what circumstances it's efficient. I think it's useful for us to have sanity checks or things like this that we can compare against. And I think that's a very good point for as we push to gauge theories. Yeah, I agree. Right. Yeah. Yeah. So good. So I will be maximally honest. I do not fully understand functional normalization group, especially I do not understand kind of the systematics or the sizes of corrections, which I mean, maybe they do. Like this is a pure statement of ignorance on my part. What's nice about this is that like here we have a very kind of very concrete understanding of our systematics and the effects of these higher dimension operators, precisely because they're just controlled by kind of these off diagonal matrix elements. And those are just controlled by kind of the large delta behavior of OP coefficients, which we have very detailed information about kind of their asymptotics. And we can really understand the size of these corrections and the rate of convergence of our our results as we vary delta max. Now, I don't know. Yeah, go ahead. I mean, good. So like, so yeah, so you're asking exactly the right question. Like, I think, so I'll say two things. One, definitely we don't, like, if we say go through a phase transition or things like this, like we currently do not have any sort of rigorous understanding of kind of our errors. What we've found so far is that the kind of observational results agree with the kind of convergence that you would find, the kind of naive convergence. But I agree that it's something that I personally would like to understand much better and much more rigorously. Yeah, that's a very good point. Yeah. Mm-hmm. Right. Yeah. So good. So yeah, what you would, I mean, yeah, exactly. So like very roughly, here's what I would hope to find. But again, like this is, we haven't done this, so like this is my hope, or what I would hope to see. So what I would expect is basically the following: is that as I like vary the number of flavors that I gap out, what I would expect to find is, say, like, let's say, you know, I start with this theory with 16 and I gap out like a single flavor or something like that. What I expect to see is some flow, and that the gap, like that, as I vary my truncation, as I add more and more states to my basis, that just my gap continually closes. That I see that I'm still in a fixed point. Maybe I'm not. Maybe I'm misunderstanding your question. But then the expectation would be that as I increase the number of, as I gap out more and more flavors, that I would then see that there's kind of this transition from and perhaps the convergence will get slower with like delta max, but I should see that once I'm outside of the conformal window, once I've gapped out enough, that really like kind of the lowest eigenstate is robust. That as I increase the truncation, he's no longer varying, that he's hitting some wall, which is the confinement scale. And then I should also see kind of roughly, like I have a prediction of roughly where I expect this scale to be, set by the coupling of the UV fixed point. Yeah, so good. So absolutely. So like, so one thing you can do, so like, for example, like one simple thing we could do is, there's probably more efficient ways of doing this, but like one thing we can do is we can look at, say, like correlation functions or something like this. And so we could see exactly this. So what we would see is that, like, let's say I went from 16 to 15 flavors or something like that. And so if I look at, say, psi bar psi or whatever, name an operator that you want to study with like some particular quantum numbers, I'll see that in the UV, it'll have some power law behavior. And then in the IR, that this will transition to some other behavior. And I can read off the anomalous dimension from there. It's possible there's more efficient ways of doing it than that, but that's kind of the most naive way that you could imagine